about the series resonance. We discussed about the resonant frequency, Q factor, bandwidth, and so small deviation in resonant frequency. So how the current is affecting. So that also is seen. So now we'll move to the next chapter and next topic. So that is parallel resonance. Parallel resonance. As the name indicates, so this resonance is occurring in parallel circuits. So let us assume that you have a parallel RLC circuit. Say this is R, so this is JXL, and this is minus JXC. So this is energized by some voltage source V, and here you have circuit current I. Since this is a parallel circuit, right? So we need to solve this one by using admittances. Okay. So we need to solve this one. So by using admittances. So here, so if we assume that all are ideal components, the admittance of the resistive branch. So what is the resistive branch admittance? So G equal to 1 by R, right? So what is the admittance of this inductive branch? So BL. So what is the admittance of inductive branch? It is 1 by J into XL. So which is minus J by omega L. And admittance of capacitive branch BC. So that is minus 1 by J into XC. So which is equal to 1 by it is J by, right? So J by 1 by omega C. So which is equal to J omega C. So we are representing in form of admittances. Okay. So the overall admittance Y, so which is equal to G plus J into, so this one, so this BC minus BL or BL minus BC, so depending on that. So here this is equal to 1 by R plus J into omega C minus 1 by omega L. So this is the admittance, right? But in case of resonance, but the circuit is at resonance, so when the resonance is happening, so this imaginary part, so whatever this J term, so this is equal to 0 at resonance. Right? So equate this to 0, so omega L minus omega C minus omega L equal to 0. So the frequency will be the resonant frequency. So that's why you have omega R here, omega R here. So that means at resonant frequency. If you equate this one, so what you will get omega R equal to, what is omega R? What
root
is omega
LC.
R? 1 by
root LC.
1 by root LC. In other words, FR equal to 1 by 2 pi square root LC. What is the formula for series resonance? What is the formula?
Same formula. Same formula.
Right? So whether it is series resonance or a parallel resonance, the formula remains same. The formula remains same. What is the difference here? What is the difference here? So here at resonance, right? At resonance, so why admittance at resonance? What is the value of admittance at resonance?
1 by R.
1 by R.
That is G, so which is equal to 1 by R. Okay. So that means the admittance will be minimum at resonance. The admittance will be minimum. If this admittance is minimum, that means the impedance will be, so Z will be maximum. So Z will be maximum. If Z is maximum, the current I, the supply, the overall current I, so which is equal to V by Z, right? So V by Z. So what is this one? Will it be minimum or maximum?
Minimum, sir.
Minimum,
So
sir.
it will be minimum.
Minimum.
So that is the difference. In case of series resonance, so Z will be minimum, I will be maximum. Okay. So Z will be minimum, I will be maximum. But in case of parallel resonance, so Z is maximum and I is minimum. So another thing is that in case of series resonance, the voltage across the capacitor or voltage across the inductor is multiplied by how many times?
QR
Q
quality
times or QR times, right? So here the current through the inductor and the current through the capacitor is multiplied by QR times. Okay, so this series resonance and parallel resonance, so both are analogous. So both are analogous. Okay, if your current is involved, so in that case voltage is involved. If this is maximum, so that will be minimum likewise. Okay, so this is series resonance, sorry, parallel resonance. So both will be same. But the thing is that, so here the assumption is, so this capacitor and inductor, so both are ideal. Okay, so both are ideal. So here, so these things will never arise practically. This thing will never arise practically. This is not a practical circuit, but whereas in the series resonant circuit, so whereas this circuit, so it is more practical. So why? Because the loss component is of the inductor especially, so that is shown here, or that is reflecting as a series resistance. Okay. So this may be R plus, or this is the original resistance plus the resistance of the inductive circuit, right? So this is practical or more practical. So whereas this circuit is not practical because of the presence of this capacitor or the inductor. So these are associating with some loss components. So how the practical circuit so will look like? It may be something like this. So we have an ideal capacitor on one side and a resistor along with a inductor. So this R here, JXL, and this is minus JXC. So this is a practical circuit. So this is all known as RLC parallel network. RLC parallel network. So meaning RL, so both are in series, and this L is in parallel. So this is basically this entire thing. So basically represents a coil, right, in parallel with a capacitor. In parallel with a capacitor. So this is the most common, or this is the most commonly possible parallel network. Right? This is the most commonly possible parallel network. Right. So now we will find out. Now we will find out the resonant frequency for this particular circuit. Okay. So let us assume that, so this is series circuit, right? So what is the admittance of this series circuit? So we'll call this as coil. Okay. So this is coil. So what is the admittance of this coil?
1
So
by
it will
R
be
plus
R plus
JXL.
JXL, right? So how to write this one?
R minus JXL by R square.
By R square plus omega square L square. So that is real part. J omega L by R square plus omega square L square. Is this correct?
Yes, sir.
Is this correct?
Yes, sir.
Similarly, Y of capacitor. So this is 1 by J. What is it? jxc, right? So what is this value? J omega c. Agree? Earlier,
Yes, sir.
yes, we done this, right? So what is the overall circuit admittance? So sum of these two, so R plus R square plus omega square L square. So that is the real part plus, right? So J into so omega C minus, what is the other part? R square plus omega square L square. Agree? This is the one, right?
Yes, sir.
Okay. So this is the one, right? So now, right, if you want to find out the resonant frequency, so so this imaginary term, so this imaginary term is equal to 0 at FR, right? So now equate this one at FR, at resonant frequency. So this will be omega RC minus omega RL by R square plus omega R square into L square, so which is equal to 0. Clear?
Can you repeat that part again, sir? Why are we imagining at 0? Why are we imagining that at 0?
That is a fundamental thing in finding out the resonance, right? At resonance, the imaginary part will be 0. The circuit is predominantly resistive only, right? So that's why you are equating the imaginary part to 0 at resonant frequency.
Yes, sir. Yes, I got it.
So that is the basic definition of resonance. Understood? Okay. So now find out. So from this, find out omega R value. So tell me, what is omega R?
Sir, omega r is called root of
Root of
L cube by L cube
Mhm.
minus RL square
Mm.
by CL square. I got that one.
That is correct, but if you rearrange this one,
Sir, 1 by L into root of L by C minus R square.
1 by LC, so it will be something like this. So R square by L square you will get. Check it once. It may be correct.
Yes, sir. Yes.
Okay. If you rearrange this one, so you'll get something like this. Got this one?
Yes, sir. I got.
So this is simple, right? So here, so if you equate this one, so you will get something like that: omega square R L square, so which is equal to L by C minus R square. So you will get this expression, right? Okay. This is the expression you got, right? If you multiply, so these things, also you will got this one. So from this, so you'll get this expression. Everyone got this one?
Yes, sir.
Yes, sir.
Okay. So from this, what is FR? What is resonant frequency? So it will be 1 by 2 pi. Okay. So 1 by 2 pi square root 1 by LC minus R square by L square. This is the one, right? What is the difference between the previous one and this one? So previous one, so that is FR equal to 1 by 2 pi square root LC. So that is 1 by 2 pi square root LC. But so you have the presence of resistance here, right? If you substitute resistance R value 0, so in that case, so both will be same, right? Agree?
Yes, sir.
If substitute R value 0, so both will be same. So this is the resonant frequency of a practical. So this is the resonant frequency of a practical parallel RLC circuit. So this is a practical RLC circuit. So at this point of right. So what is YR? What is the resonant frequency? What is the resonant impedance at resonance?
R by
Impedance at resonance.
R by R square plus omega square L.
What is that? R by R square plus
Plus omega square L
L
square.
square, right? Okay. So this is admittance at resonance, right? So this is known as admittance at resonance. So earlier, what is the admittance at resonance? It is 1 by R. So now it is changed to R by R square plus omega square into L square. So this entire thing is a resistor circuit, right? So this entire thing will form a resistor circuit, right? So this also can be seen here. This is the imaginary part is over, right? So this is the real part and we have imaginary part. We made that imaginary part to 0. Okay. So here, so this is changing with this resistance R, right? So this changing with resistance R. So that's why in some cases, so they will call this as a dynamic resistance. RD, dynamic resistance RD, right? Since this current is at resonance, is in phase with the voltage, so the impedance of this network, so it acts as a resistance, right? So this resistance is known as dynamic resistance, right? So how this dynamic resistance is calculated? RD equal to V by IR. So V by IR, so where this IR is the resonant current. Okay, so this is known as, right? So this IR, so what is this IR? So this is V into YR. So YR is the admittance at resonance. So it will be V into R by R square plus omega R square into L square, right? Okay. So from this, so what is this RD value? So this RD value will be R square plus omega R square L square by R. Both are same, right? We have admittance at resonance, so which is equal to, what is the admittance at resonance? R by R square plus omega R square L square, right? So from this, what is the impedance at resonance? So that is ZR, so that is R square by R square. So this is predominantly resistive, or this is resistance, right? So that's why this is also known as dynamic resistance. Okay, so this is known as dynamic resistance. Okay, so we can rearrange this one.
Called dynamics one.
Why called it's dynamic means here in case of series RLC circuit, right? So you can easily say that, so that is equal to resistance of the circuit, right? Because every time the circuit configuration changes, so this value will change. Okay. So here, if you notice that in case of series resistance, that only depends on the resistance. So not on this capacitance value or not on this inductance value. If you notice that, so this values depends on this L also, right? Okay, and this is also
Yes, sir.
depends on this resonant frequency also. Whereas in series resonant, right? Whereas in series resonance, so that is depends on only R. So there is no omega term, so there is no L term and no C term. Understood? So that is
Yes, sir.
independent of inductance, capacitance, and resonant frequency. But whereas in parallel resonance circuit, so that depends on this omega or L. If it is in parallel, if the resistance, if you consider the resistance, so here also if you consider resistance here, so that is also comes into picture. So therefore, so every time it will change with when we change the resonant frequency. So that's why it is known as dynamic resistance. So that's why it is known as dynamic resistance. So later we'll see that. So this is all depends on L value, LRC values. So that we'll see now. So if you decom or if you if you separate these terms. So earlier, so we have this R square by R into L square. So this omega R can be written like this, right? So how this omega R is written in this? This is the one we obtained, right? So from this, what is omega R square? What is omega R square?
1 by LC minus R square
1
by
by LC minus
R
R
square.
square by
by
L
L
square.
square.
Okay. So we'll bring this here 1 by LC minus R square by, what is that? R square by L square.
Yes, sir.
Sir.
Right. Separate this one. So this R square plus, what is the next term? L by C.
Yes, sir.
Yes, sir.
What is the next term?
Minus R square.
R square.
Minus R square. So divide by R, right? So what is the overall one?
L by
By
CR.
RC.
L by CR or RC. So what is the dynamic resistance RD? So it is L by C into R. In case of series resonant circuit, so we will not call this as a dynamic resistance because it only depends on the resistance of the circuit, right? Okay. In ideal case, right, if this is the ideal RLC parallel circuit, so in that case, the dynamic resistance RD equal to 1 by R only. Okay. So this is for ideal RLC circuit. So this is for RLC circuit. Okay. RL both are in series, right? For that combination, the capacitor is in parallel. If the circuit changes, if something, sorry, for example, if you are incorporated a resistor here, so in that case the dynamic resistance will change. So this is for the dynamic resistance RD is for L by CR. So whereas in previous circuit for this dynamic resistance RD so is equal to 1 by R only. Understood? Right. Okay.
Sir,
So next, yes.
sir, in previous one ideal one, sir, dynamic resistance will be R, no, sir.
That's why. Okay. Is it R or which one? This one. Yeah, it is one.
Yes,
Yeah,
sir.
this is R only. Yeah, sorry. So this is R only. The dynamic resistance is R only. Right. So RD equal to R in case of ideal RLC circuit, parallel circuit. Okay. So next we have more practical circuit, right? So we have more practical circuit. So that means the circuit will be something like this. In generalized parallel. So this is RC, this is RL, so this is JXL, and this is minus JXC. So this is the voltage, and this will be the current. Okay. For this particular case, so how you will find out the parallel resonance? Okay, so how you will find out the parallel resonance? So that is important, right? So here, this entire thing, so YL, what is YL? So that means the admittance of this one, and YC, and you need to calculate Y. So what is YL? 1 by RL plus JXL. Okay. So this is 1 by RC minus JXC, right? Agree? Agree?
Yes, sir.
Okay. So here from this Y, straight away I am writing. So what is the first term? So this RL by RL square plus JXL square, right? No, not JXL. So it is XL square, right? In other words, omega into L square. Is this correct? Minus JXL by R square plus XL square, right? Second one is RC by RC square plus XC square plus, right, this is plus, right, minus JXC by RC square plus XC square. Is this correct?
Yes, sir.
Yes, sir.
So imaginary parts we need to equal to 0. Imaginary parts we need to equal to 0. So imaginary parts is minus XL by RL square, just XL square. Okay. Next one is XC, right? RC square plus XC square, which is equal to 0. So substitute XL place, you need to substitute. If XL equal to omega RL and XC equal to 1 by omega R into C. So you need to substitute those things, right? I will write the final expression. It will take a few more steps. You just solve this one, right? If you find out the resonant frequency, it will be something like this. So 1 by 2 pi square root LC. So this is the original one. RL square. Sorry. RL square minus L by C by RC square minus L by C. Okay, so this is the final formula. So when you have, this is the generalized circuit. So this is the resonant frequency FR equal to 1 by the square root LC, RL square minus L by C, RC square minus L by C. If RL, RC values are 0, so that is equal to 1 by 2 pi square root LC only. Okay, so that is equal to 1 by square root 2 pi LC only. Okay.
So do we have to remember this or we can solve in?
These are just simple things only, right? You have to solve. If you need to remember these things, okay? Or else you need to derive these things. You need to remember. That's all. To some extent, you need to remember. So can anyone tell what is dynamic resistance RD? What is dynamic resistance RD? In this particular case, what is dynamic resistance RD? What is RD? What is dynamic resistance RD? You need to simplify. You tell me what is RD. What is the real part of this Y? What is the real
RL by
part of
RL
this Y?
square plus XL square
So
plus.
this term and this term, so these are the real parts, right? Okay.
Yes, sir.
So that means this is the circuit or the admittance at resonance, right? So 1 by admittance at resonance. So that is gives you the RD, right? Okay. Understood? So sum of these two, so that gives you the admittance as resonance. Okay. So that means its value is 1 by RL square plus XL square plus RC by RC square plus XC square. So that is its value. So these two will formulate, the addition of these two will formulate YR. Okay. So 1 by YR, so that gives you RD. Understood? You have any questions?
No, sir.
Right. So next we'll consider for Q factor. Q factor at resonance, right? In case of series RLC circuit, so this Q factor is a measure of voltage magnification, right? It's a measure of voltage magnification. But in case of parallel RC, parallel resonant circuits, so this Q factor is a current magnification. So it is a current magnification. So the current through the inductor and the current across the current flowing through the capacitor, so will be multiplied by Q times. Okay. So this Q factor, so this QR, in case of this RLC circuit, so this circuit, so this can be written as RC hyphen RL circuit. So meaning is RC, so both are in series, RL, so this is also in series. So these two are in parallel. So that hyphen usually represents the parallel form. That's just simplified representation for our understanding. Okay. So this QR for this circuit. So what is QR? So basically the current through the capacitor current by current at resonance. Is this okay? This formula? That is the one we required, right? So that is the capacitor current IC by IR. So this only gives you QR, right? Understood?
Yes, sir.
Okay. So we know that the capacitor current is multiplied or magnified by QR times resonant current. Okay. So now what is IC? What is IC? If you know the voltage, what is IC? So this IC is, we can write V by XC. Agree?
Yes, sir.
What is resonant current? Resonant current is V by RD. Agree?
Yes, sir.
V by RD, right? Okay. Right. So it will be, so V omega R C. Okay. So it will be V into, what is RD? What is RD? C
So L upon RC.
L upon RC, right? So what is this entire thing? Is it omega R L by R? V get cancelled. Okay, C get cancelled. So you're left with omega R. that thing, right?
Yes, sir.
So this is same expression as series resonance, right? So this is the same expression as series resonant. The QR formula is remains same. So this is same as series resonance, right? For series resonance also, so we have same expression. The series the series resonance, we have the same expression. There is no change in the value of QR. So there is no change in the value of QR. Similarly, the other terms, right? If this QR is known to you, so we have this upper and lower off power frequencies, right? Or else QR can be written as FR by F2 minus F1, right? So here also bandwidth is F2 minus F1, or FR can be written as square root of F1 F2, square root of F1 F2. All the formulas, whatever we derived, so all are same. The thing is that this F1 and F2, so these are the off power frequencies. These are the off power frequencies. So where the admittance is, what is the admittance at F1 or F1? Can anyone guess? What is the admittance of F or F1? What is the admittance at resonance? What is the admittance at resonance? What is the
R
admittance
upon
at
R
resonance?
square plus omega square L square.
Right. So that is equal to 1 by RD, right? Agree?
Yes, sir.
Okay. So now what? Tell me, what is the admittance at F1 or F2? So will it be root 2 times 1 by RD? Agree?
Yes, sir.
So that is the
Yes,
basic
sir.
thing, right? Okay. So that means whatever that imaginary part and real part, so both are same. Imaginary part and real part, so both are same. So that's why, so this is root 2 into 1 by RD. So if you remember this, right?
Sir, admittance will be 1 upon root 2 RD, right?
No, the admittance value will be increased, right? So earlier the admittance is the minimum one. Okay. At resonance, the
Yes, sir,
admittance
yes.
is minimum. Okay. But that is the minimum possible value, right? So it can't be 1 by root 2. So that is the minimum possible value. So understood the difference, right? So this is the minimum possible value, right? So that means the curve will be something like this. I will draw the curve. So this admittance curve
So could you go to
will
the
be
previous
something
slide?
like this. Okay. So this is, what is this value? 1 by RD. Okay. So that is admittance 1 by RD. So this is your F1 and this is your, somewhere you have your F2. So now what is this value? 1 by RD into root 2. Understood? No confusion, right?
Yes, sir.
Okay.
Sir, I
So
didn't
no
get that
confusion,
part,
right?
sir.
Yes,
Root
yes.
2 upon RT. Sir, I didn't
What
get
is-
that part, sir. Admittance is equals to root 2 upon RT.
So here this is admittance, right? Okay. So here earlier case, so you have, this is impedance, right? This is series resonance. So the curve is also, so it is same only. Okay. So what is the value here? So this is R, right? Agree?
Yes, sir.
So this one is root 2R and this is corresponding to F1, F2. This is corresponding to FR and this is corresponding to F2. So this is corresponding to FR, right? The same thing. So here the thing is that this is an admittance, so this is impedance only. So this is the minimum possible, right? So this is where the imaginary part is equal to the real part. The imaginary part is equal to the real part. We have derived this, right? So this is R, so this is also R, and this will be root 2. Okay, where this omega L minus omega C, so this value we are equate to R, right?
Yes, yes, sir. Got it, sir.
Now understood. So everything is same. So because both are analogous, right? So this thing and this thing is analogous. So earlier you have impedance, so now you have admittance. So remaining rest of the things are same.
So means if in this case also Q is greater than 10, then we'll assume symmetry.
Yeah, Q assume symmetry. That's true. That is true. So here also we have some formulas that are derived, right? If the deviation is delta, so we derived some formulas, right? Can anyone tell what is this formulas? We derived some formulas. We derived some formulas, right? So what are those? What are those formulas? I by IR. What is I by IR? Or in other words, what is Z by ZR? What is Z by ZR?
1
1
plus
plus
2
J
sigma
1
J
plus
So 1 plus
sigma
J
J
to
QR.
rho
delta
QR.
Q,
Rho
right?
QR.
QR or Q, right? So this delta is positive for if the gradient frequency is above FR, and so positive for above, negative for below FR, right? We
Yes,
derived
sir.
this, right? Similarly, right, so in the same way, so this now will be Y by YR, okay, Y by YR, so this is equal to 1 plus J 2 delta QR. Okay, 1 plus J 2 delta QR. Everything is remains same. So the thing is that it will be 1 by J by 1 plus J into 2 delta QR. Understood? So now tell me what is I by IR? Can anyone tell what is I by IR?
1 plus J2 delta QI.
What is I by IR? In case of normal circuit, what is I by IR? It will be 1 by
So 1
J,
upon 1
1
plus
by
J2 QR
J2
delta.
QR delta.
J 2
2 QR.
delta QR, right? So now tell me what is I by IR? This is in case of series circuits. In case of parallel circuits, what is I by IR? Will it be same or different? What is
Same.
I? What is I is V, right? I can be written as V into voltage V into
Admittance Y.
admittance Y, right? So this can be written as V into
IR.
YR, right? So that means
Yes.
so both are same only. No change, right?
Yes, sir.
Okay. So when you know the V by VR, right? So this V by VR is this one. Is this correct? Just check out that. So tell me whether it is correct, right or wrong if you have doubts. So next thing is, okay. So next thing is we had different resonant frequencies are there, right? So first thing is, in case if you talk about the ideal RLC circuit, so the resonant frequency FR is 1 by 2 pi square root LC. We have series RLC circuit, so this resonant frequency is 1 by 2 pi square root LC. But we have parallel RLC circuit. So what is the resonant frequency here? 1 by 2 pi. What is its value? Square root 1 by LC minus R square by L square, right? Is this correct?
Yes, sir.
Okay. So now, so we will find out the relation between these two. Right. So generally, right. So generally, so this resonant frequency or this ideal resonant frequency, so this is known as natural, right? So this is known as natural frequency of resonance, right? So this is known as natural frequency. Most of the times we'll denote it with Fn. So this is known as natural frequency or natural resonant frequency. So whereas this one, right? So whereas this one, so this is sometimes, right? So this is sometimes represented a forced resonant frequency. So this is sometimes represented as a forced resonant frequency. So for any circuit, the basic formula for the resonant frequency is either this one or this one. But the thing is that because this circuit will never exist, this parallel RLC circuit will never exist. So that's why, so we are forced to modify the circuit. So that's why it is known as forced resonant circuit. So that's why it is known as forced resonant circuit. So now we'll change this one as, so we'll talk this one as Fn, so which is equal to 2 pi square root LC. So this is as it is Fr, so that is the resonant frequency. So now we will do this operation Fr by Fn. Fr by Fn. So what is Fr by Fn? If you do Fr by Fn, this is Fr and this is Fn. If you solve this one, it will be 1 by LC minus R square by L square by 1 by square root LC. Is this correct? Is this correct?
Yes, sir.
Okay.
Yes, sir.
Right. So we will modify this one, square root of 1 by LC minus R square by L square into square root LC. Is this correct?
Yes, sir.
So this can be written as square root of 1 minus R square. No. Is this R square C by L? Is this correct?
Yes, sir.
Okay, R square C by L, right? So, but with the resonant frequency, this Q can be written as 1 by R square root L by C, right? So this is another formula for resonant frequency. You're aware of this, right? You're aware of this formula, right?
Yes. Yes, sir.
So from this, so what is Q square? So this is for Q factor formula. We derived this Q factor, right? 1 by
Yes,
R
sir.
into square root L by C. You're aware of this, right?
Sir, this Q factor is for parallel RLC, sir.
We have discussed that per Q factors remain same for either series RLC or parallel RLC. We derived this formula somewhere. I hope we derived this formula, right, for Q factor.
Yes, sir. We derived it.
Okay, right. So this is QR, right? So what is Q square? What is Q square? So it is 1 L by R
1
square C, right?
L2. Yes, sir.
Agree?
Yes, sir.
So this thing can be written as, how to write this one?
1 by Q square.
So 1 by Q square. So this entire thing can be written as square root of 1 minus 1 by Q square. Now QR, so resonant, so more precisely. So this is equal to FR by FN. FR by FN. So now, so usually this QR value, so usually, right, in case of electrical circuits, it may be 1.5 or something like that, 1.5 or 2. But in case of electronic circuits, as we already discussed that, it is greater than 10, right? If this QR is greater than 10, right, if QR is greater than 10, what is FR by FN? For example, QR is, for
Sir,
example,
almost
QR equal to
1.
10, right? So if QR equal to 10, what is this value? 1 minus 1 by 100, right? Agree?
Yes, sir.
So this will be
Yes, sir.
0.01. So that means square root 0.99. So what is the difference between these two? Or what is the difference between this FR and FN? What is the
Square root of
difference? So
100.
it is almost minute, right?
Yes, sir.
Yes, sir.
If for example, if FR equal, if QR, for example, this is 100, if QR, if you consider this is 100, right? So in this case, the difference is almost, or there is no much difference, right? So there is no much difference. The thing is that, so here, if the QR value, if the Q factor is very high, the Q factor is very high. So here this Fn, the natural frequency of resonance and the forced resonance frequency Fr are this one. So both same, both are more or less same. There is no much difference, or the difference is same. So high value of Q makes the parallel resonant frequency tend to be same as that of the series resonant frequency. Okay. So that means parallel resonant frequency and series resonant frequency. So both will be same if you choose the Q value high. So normally we'll choose the Q value high. So that means these things, so the significance of this one and the difference between this one is almost minute if you choose a large value of Q. Understood? Clear?
Yes, sir.
Yes, sir.
Okay. So here, this is whenever the question is resonant frequency. So this is the formula. So this is also resonant frequency, but we are forced to operate in the resonant frequency by modifying the circuit. So that's why it is known as forced resonant frequency. But the forced resonant frequency and the natural resonant frequency, so both will be same almost when the Q value is large. Okay. So we'll stop here. Okay. So in next class, we'll try to solve some problems. You have any